Hello class 9 students, welcome back to the new videos. This video will be the last videos based on these chapters. We have already completed all the chapters explaining every topic. We have discussed about law of conservations of mass. We have discussed law of chemical combinations, law of conservations of mass. What is the law of conservations of mass says? A mass can neither be created nor be destroyed during the chemical reactions. Okay. Then we have discussed about the law of constant proportions. Then we have discussed about the John Dalton atomic theory. John Dalton atomic theory is one of the most important theories that you have to remember. What does the John Dalton theory is that he said that you have to make it recall of it. Then we have discussed what is an atom. You see, what is an atom? An atom is the smallest particle which cannot be seen with the naked eye. Okay, so this is what we have discussed about in the previous topic. We have also discussed about what are the modern day symbols of the atoms. Okay, in a different symbols that we applied. Okay, for the modern days elements. Okay, so you see, in the previous lectures also we have discussed how to give a naming to the elements. How do we give a naming to the elements? So when you're trying to write elements, keep it in mind. These are some rules that I have already discussed in the previous video lectures also, but I'm just recalling it this one. Okay, so what does it say? If you're trying to when you talk about it, before we give the symbols of any element, okay, in the ancient times, what happened? They used to give the elements that this used to be the sign for the hydrogen. Okay, this used to be sign for the hydrogens. Got it? Again, this used to be the sign for the oxygens. This is how we used to give a symbol. Okay, this is how we used to indicate the element. Okay, but days by days, these are some elements. You see, this is another element that is sulfurs. Okay, another one more element is here. So they have keep on focusing on different types of element to give a different type of symbol. But you see, the more we get advanced, the more we detected the more we discovered new elements. As I already told you, in a recent chemistry books we have, and in every book, some of them they said it is 118 elements in the universe. Okay, in some books they said it is 115 elements. Okay, so both are correct. 118 or 115. Okay, so both are correct for us. So we have 118 as an element in our universe. So how can we indicate such types of symbols for all those elements? So what we did is that we start giving the symbol and convenience. Okay, an effective symbol for every element. Like if you talk about the hydrogens, if I want to give the symbols of the hydrogens, then I have to give the symbols, the capital H. Okay, remember this one, the capital H. I cannot write hydrogen H like this. Okay, I see many students are writing in this way, H2O. So this is wrong. We cannot write H small letter 2O. Obviously, this is you might be knowing that water is the formulas of water is H2O, the small letter H2O. Or some of them they used to write like this. This should not. This is completely wrong. Okay, this is completely wrong. What does the chemistry say? The IUPAC have given the rules. Okay, the IUPAC has given the rule that hydrogen should always define by the capital letters H. Okay, by the capital letter H. Okay, it should be always defined by the capital letter H. That is what. If I want to write the waters, okay, if I want to write oxygen, then the first letters, if the oxygen is derived, if the element is derived from the English name, then we have to give the first initial name letter, that is O. Oxygen is derived from the English letters. Okay, English word. That is why we define by we denote it by the capitals O. Now, if I want to write the waters, the formulas of water, we know that we always used to have waters. The formulas of water is what? H capital, and 2 should be written in the suffix. Okay, in the down here, then O here. Okay, you cannot write like this. You cannot write like this. H2O or H2O. Okay, Some are writing this all very small, right? So it should not be done. This rule should be there. So these are some where we used to do a lot of mistakes. Okay. Another thing that we do is that now when you talk about a calcium, okay, calcium, what is it? Calcium, the formulas is calcium is what? The formulas of calcium is capital first letter C, okay, and the second letter should always be a small letters, that is CA. Okay, but some of them they use letters C capital A or C capital A. These are all wrong. Okay, some of them they say when you talk about the calcium carbonate, this is also wrong. Okay, so what you have to write, calcium is an element, Ca. Carbon is an element, that means C should be capital. Carbon and O is an element, that means O should be also a capital letters, that means CaCO3. Okay, this is how we have to write. So from now on you are very familiar how to write the chemicals, element, chemical formulas. Okay, and how to give the symbols of all those elements. You see some of them they use to write this way also. Sodium. Sodium, we know that the formulas of sodium is what? Na. Okay, why is Na? Because the sodium is derived from the Latin word called natrium. Okay, so that is why you derive from the Latin word called natrium, that is why Na. Okay, so N is capital letters, N is capital letters, and A is a small letters. Okay, so when we are writing this one, some of the students they used to write this way, Na. Or some of the students they used to write Na. Some of the students they used to write N capital A. Okay, these all are wrong. Always remember the first letter should be a block letter, that is capital letters, and the second letter should always followed by the small letters. Okay, so always keep it in mind. Whenever two elements are combining, if the two elements are combining, let's say, let's say NaCl, sodium chloride. Okay, when you're sodium chloride, if the two elements are combining, sodium chloride. If the two elements are combining sodium chloride, sodium we know Na, chloride we know Cl. C is capital letters and L is small letters. We have to write it this way. Okay, C is capital letters and L is small letters. NaCl. Okay, some they used to write only this one. Okay, so NaCl. Got it? But what happened? Most of the students they used to write NaCl. NaC is also small, L is also small. This is wrong. So N is capital letters, A is sodium. That means if N capital letters then followed by small letter, remember this is one element. Okay, capital letters followed by small letter, that means this is one element like sodium. Na is sodium. Okay, similarly chlorine, C is capital letters and then L is small letters. Okay, C is capital letters, then L is small letters. Okay, C is capital letters, then L is small letters. This is what NaCl. Okay, but if you talk about another element like carbon dioxide, okay, carbon dioxide, many students used to do the mistakes when writing the formulas of carbon dioxide. Obviously, whatever you're writing, whatever you're taking, CO2 is correct. But how you define, how you show, okay, how you represent, that is mistake. Okay, so what is most of the students used to write like this. Okay, most of the students they used to write like this. So what is it? C is capital letters and L is always small letter. That's wrong. Okay, it is completely wrong. Whenever you are writing carbon dioxide, C should be capital. That means C is carbon and O should be also capital letters. There is no running in. Okay, you should not run. Okay, there's not it should not be writing running handwritings. Okay, it should not be. The C should be capital letters and O should be the capital letters then too. That means C defines that this is carbon and capital O also let us know that it is an oxygen. Okay, but if I talk about CO become a cobalt. Okay, some other elements again. So that is what you have to make it, keep in mind while writing the chemical formulas of chemical compound. Okay, so what is the capital letters, what is the small letter, you have to be very clear about it. Okay, next thing you see in the previous topic, if you go to the page number 34, or your question will be written in your in the screens also. Okay, in a reaction, 5.3 of the sodium carbon reacted with 6 grams of the ethanoic acids. The product were 2.2 gram of carbon dioxide, 0.9 grams of water, and 8.2 grams of sodium ethanoate. So that these observations are agreements with the law of conservation of mass. Okay, so what does it say? So you see, this is the formulas given, this is a question given in your test box. Okay, so what does it say? You see, 5.3 grams of sodium carbonate. Okay, so mass of before reactions, before reactions, mass of sodium carbonate, mass of sodium carbonate is already given as 5.3 gram. Okay, mass of sodium carbonate is always given as sodium carbonate is 5.3 gram, and mass of ethanoic acids. Ethanoic acid is how much? That is 6 gram, if I'm not wrong. Okay, 6 gram. Yes. Now, then total mass before reaction is what? Total mass before reaction is what? Total mass before reactions means before they undergo reacting. Okay, this is before reacting. This is what they call a reactant. They will try to react. When they react, you will get a sodium ethanol, carbon dioxide, and waters. Right? Sodium carbonate react with ethanol. So before we go to reaction, before you make a tea, you take a sugars one and amols dudes. Okay, so whatever it is, before we go to reaction, the mass before the reaction is what? 5.3 gram plus 6 gram is how much? 11.3 gram. 11.3 gram. Now, after the reactions, you see, after reaction, what is the product we got? Before reactions, we have reacted sodium carbonate and ethanoic acids. But after reacting, we are getting sodium ethanoate, carbon dioxide, and waters. Okay, so mass of what is it? Mass of sodium ethanoate is equal to mass of sodium ethanoate is equal to 8.2 gram. 8.2 gram. And mass of what is it? Mass of carbon dioxide. I'm writing the formulas. That is how much? That is carbon dioxide is 2.2 gram. And mass of water is how much? That is equal to 0.9 gram. 0.9 gram. Now, total mass after reaction is what? Total mass after reaction is what? Sum of all this. That is what? Sum of 8.2 plus 2.2 plus 0.9. What is the answers? 11.3 gram. You see? Mass of total mass before after reaction, what is it? Total mass after reaction, what is it? Total mass after reaction, what does it say? Total mass after reaction is what? 8.2 plus 2.2 plus 0.9 is equal to 11.3. Before reaction also it is 11.3 and after reaction is also 11.3. That is what? This saw the law of conservation. Okay, law of conservation is said that a mass can neither be created nor be destroyed in a chemical reaction. Mass can neither be created nor be destroyed in a chemical reactions. Okay, so this is what is so. This is what is so in the question number, page number 34, question number 1. Okay, your question is already written in your screen and has also been displayed in screens. Okay, next, we'll go to next question number 2. Okay, next, hydrogen and oxygen combine in the ratio of 1.8 by the mass to form a waters. Okay, so what is it? A mass of what is it? Mass of hydrogens. Okay, combine mass of 1 hydrogen combined with mass of 8 oxygens. Okay, so what will be the mass? What will be the mass required to react with completely with 3 grams of hydrogen? How much mass of oxygen is required to be completely reacting with 3 grams of hydrogen? Okay. The question is written on your screens also. It will be displayed in your screens also. Okay. So what is the mass of oxygen required? Mass of oxygen required to react completely with 1 grams of oxygen. The ratio is given. Question number 2. Ratio is given. The ratio hydrogens, okay, the ratio, what is it? Hydrogens is to oxygen. Hydrogen is to oxygen, that is how much? 1 is to 8. Okay, this is what is given by mass. Then the mass of oxygen that required to the mass, then mass of oxygens required to react completely with 1 grams of hydrogen is how much? Okay, in order to react 1 grams of mass, in order to react 1 grams of hydrogen, we need how much grams of oxygen? 8 grams of oxygen. Okay, that means mass of oxygen requires to react completely with how much gram? Question, how much gram? It is 3 gram. 3 grams of hydrogen. It will be what? 8 into 3 gram, that is how much? 24 grams of oxygen is needed. How many grams of oxygen is needed? 24 grams of oxygen is needed to be completely react with 3 grams of hydrogens. Okay, that means what? You can also write mass of 1 grams of hydrogen is equal to 8 grams of oxygens. Okay, mass of 3 grams of hydrogen is equal to what? 8 into 3 times of 24 grams of oxygens. Okay, so this is how the question is. You can note it down. Mass of oxygen required to react completely with 1 grams of hydrogen is 8 grams, and mass of oxygen required to react completely with 3 grams of hydrogen is what? 8 into 3, that is 24 grams of oxygen is required. Okay, 24 grams of oxygen is required to react completely with the 3 grams of hydrogens. Okay. Okay, let's go to the next exercise, that is page number 45, question number 1. Okay, this question is number 1, also it will be written in questions, okay, in your screens. Okay, you can just check out the screens, or you can also refer to the page number NCRT NBSC core page number textbook, science textbook, page number 45. Okay, the first question said 0.24 grams of simple compound of oxygen and boron was found by analyzing the content of 0.96 grams of boron and 0.114 grams of oxygen. Calculate the percentage of compositions of compound by the weight. Okay, so we have to find the percentage of the compound. Okay, so here's the question number 1. You see, solutions given mass of the samples. Mass of sample, that means what? Mass of sample is the combinations of boron, B and carbon. Okay, that's equal to mass 0.24 gram. How much? 0.24 gram. Yes, 0.24 gram. Again, mass of boron is given. Boron, that is B, denoted by capital B. That is how much? 0.096 gram. Again, mass of carbon. Carbon is also given as denoted by C, that is 0.144 grams. Okay, so you're asked to find the percentage of carbon, you're asked to find the percentage of oxygens, boron separately. Okay, you're asked to find the percentage of carbons and okay, for boron. Percentage of the boron by weight. Okay, percentage of boron by weight. Percentage of boron by weight. The percentage of therefore the percentage of boron by weight. Percentage of boron by weight in the compound. Is equal to how much? In the compound is equal to how much? Percentage of grams of boron is much 0.96 and total mass of sample is how much? 0.24 into how much? 100%. So divide these two. You try to divide these two. Okay, so if you are dividing these two, you will get nearly 40%. How much? 40%. Okay, you will get nearly 40%. Then next you will find out the for carbons. Okay, so if boron is 40%, then easily we can find out the percentage of carbon by subtracting 100 minus 40, it will become 60. But still here also we can do it this way also, or we can do it here. Percentage of, I can write percentage of carbon by weight in the compound. So what is it? Total weight of the carbon is how much? 0.144 and divided by 0.24 into 100. Multiply and divide this equation, then you will get nearly 60%. So carbon mass of the percentage of the boron is 40, mass of the percentage of carbon is 60. So if you add up, that becomes total 100, right? That becomes total 100. So this is how we find the mass of the carbons of the compound. Okay, this is how we find the mass of the carbon of the compound. Okay, so this is how we do. So as much as possible you try to solve it, all the remaining questions, and I've already told you. So your homeworks, okay, you have to submit your homeworks in the next Monday. Please submit your homeworks, that is page number 41, question number 1, question number 2. Okay, so I will just note it down on the screen. Okay, so what are the questions that you have to submit on the coming Monday. Thank you, stay safe, bye bye.